All right, we'll roll. So, answering Samantha's question. 19 through 21. There are questions from 15 through 18, but we'll see where we get to today. There's going to be at least one question from this section, just because we've gone over some of it. So it's possible that when they hand it down, I'll write on the board, hey, ignore question, whatever. And then I decided to do something a little bit different in the chapters of 6 through 10, and I'll talk about what I did with those. Basically, there's 2 questions. Each question has 3 parts. One of the questions is pure concept. So there's 3 conceptual questions, which I bundled up into one, just in case, because this was a little bit farther back, that it's not going to hurt you too badly if you completely blank on it. And the other one is 3 plug and chug problems. So if you know which equation to use, you plug the numbers in, don't mistype on your calculator. Such as, at this point, you should know what the formula for kinetic energy is. And so if I give you the mass and the speed, you should be able to figure out the kinetic energy. That's sort of the level. And the equations from those chapters are on the first page. So that's what the test will be on.
So no thermodynamics.
What's that?
So no thermodynamics.
Well, the 15 through 18 is thermodynamics.
Okay.
So, I mean, right now there are 3 questions on there which deal with thermodynamics, and it's possible that it will be reduced to 1. I will know at the end of today whether there's, how many are on. Kimberly?
Hey, we don't have a calculator. Can you provide us with one, or we gotta buy one?
No, I can provide you with one.
Okay.
I have batteries and everything.
Okay.
Apparently, we're able to borrow them from the bio people because apparently you don't use calculator much in biology. I know I did not use a calculator much in the late 70s, the last time I took biology.
And when will we be getting the test back? Like what we got for this one that we took right now?
The one that you took right now, they'll be graded by at the latest some point tomorrow.
Okay.
Do you want me to post it on Blackboard what you got, or would you rather?
Yeah, just post it on Blackboard. I wanna see my grade on
Okay. If you don't want to see it on Blackboard, because basically what you're going to see is just a number and not context or how many you got right. It's just what the grade is. If anyone would rather not have me post it on Blackboard, just let me know. Otherwise, I will assume Kimberly is speaking for the class. And congratulations on becoming the spokesperson. Other questions, Tana?
Did you want us to resubmit our lab from Monday in Blackboard?
No, if you send it to me through email, that's fine. It is now set up for you to be able to submit through Blackboard unless I messed that up. So.
Okay.
Other questions? Administrivia or content? Is there anything that we can do for you? You look like you've had a migraine.
I do, sorry. Oh, no, I'm fine, I'm used to it, it's much better than this morning.
Well, that helps at all. If that's too dark for people, then we can turn that back on, but I'm hoping at least that,
That's very
that
kind
helps,
of you.
5% or something.
So Monday's lab, is that due already?
Yes,
Okay.
feel free to hand it in early if you wish, or submit it early. And I've mentioned it before, and I've sent out an email, and it's in the syllabus, but please, please. It's a real nuisance to have to put in part of the naming convention, when it's so much simpler, I think, for you to do it than for me to do it for almost everyone. The big things. The first word in the name of your submission, if you're doing it electronically, is your last name. If you have a hyphenated last name, the full thing or just the first part of it. It helps me later when I'm putting grades into Blackboard that it's in order. It does help me. And also, if you're doing multiple pages, please make sure that the name is in the proper order, so that when I put the files onto my flash drive, they are already sorted in the order in which I need to open them up. Don't make me hunt. And I'm about to single one person out because I just have a question about it, so I'm gonna pause this in theory. And we're back. That's one other thing I'm gonna say before we start content. Unless there are questions. Thank you very much. Make sure I can read your handwriting. Okay. On Monday's lab, the detail that I saw most people going into, bringing out the paper clips, and it was just a little bit off, so they put on a slightly smaller paper clip or put on a slightly larger paper clip. That attention to detail, I don't see that often, especially in 110. So thank you very much. I got home, I was in a good mood, told my wife about it. She was happy that I came home in a good mood. So thank you. I do appreciate it. Okay. We're about to start content. I don't know what your schedule is, because officially we're about to morph into lab. But feel free to stick around as long as you want, or storm off when you want to.
Yeah, I found out it's early dismissal today.
Oh, for school?
Yeah,
Why?
I don't know.
They're just messing with you?
I wanna say that, but you
Okay.
know. So, they're getting out at like 1:15. Yeah. Are you gonna be posting this? You gonna be
This?
posting
Oh, yeah.
it?
Oh, yeah.
Okay.
Yeah, the other ones, I think I'm up to date in posting everything.
Mm-hmm, okay.
All right, we last left off with some thermodynamics. We had sort of dealing a lot with the change in energy, primarily around change in temperature. So we have the change in kinetic or change in potential. Change in kinetic can either be the macro or the large scale. That's the object itself is moving faster, not part of thermodynamics, but something that we've already dealt with in chapter 7. And then the change in kinetic energy on the micro level, this is the thermodynamics piece of it. And the two pieces that we are sort of looking at here is that there could be a change in temperature and a change in length. I don't know who did I remember doing this in elementary school where you take a jar and you put it under hot water, and the lid of the jar is metal. It will expand and it's a lot easier to take off. I got a couple people nodding. I'm glad that one's not dead yet. So this is coming down to this, when you put energy in, almost all things will expand. There's a small, very small group of things that will shrink under certain circumstances when heat is applied, water being one of them at certain temperatures. And then if you have a change in potential energy, from a thermodynamics point of view, you can have a change in phase. In other words, liquid to gas, liquid to solid, melting. So we dealt with, as far as we got last time, we got into basically temperature, and I did talk about specific heat, I recall. Q is the symbol used for heat. Naturally. I think it's mentioned in one of the videos. I assume it comes from the word quantity of energy. I'm not quite sure how they came up with Q, but Q is the typical letter that's used. And heat specifically is energy moving from one object to another, I'll put object in quotation marks, to another, because of a difference in temperature. So if I have a baseball sitting here and I take a bat and I swing at the ball and I hit the ball, that is not thermodynamics. There's energy change that is exchanged or sent from the bat to the ball, but it is not a change in energy because of a difference in temperature. So not thermodynamics. It's more on the macroscopic level. So as I put heat into an object or take heat out of an object, the temperature will change. That basically the molecules will start moving around a little bit faster because how fast the molecules move is directly related to the kinetic energy. And we had the formula Q is equal to mc delta T. This is the mass of the object or substance, whatever we're putting energy into. Mass of heat with the word object. This is the specific heat. And this is the change in temperature. Now, I've called C specific heat. There's another word for it, or another way of calling it. It's also called specific heat capacity. Obviously, I will go back and forth between calling it specific heat and specific heat capacity. Specific heat is just one fewer word, so that tends to be my lazy way of doing it. And not to be confused with heat capacity. Matter of fact, in thermodynamics, whenever they say the word specific, that means that you need to somehow take mass into account. Mass has not been taken into account if they use the word specific. Take specific out, and mass is already figured into it. So heat capacity would be something you would use if you're using a number where mass is already taken into account. All right, so let's do some numbers here. Because of course, everyone loves a graph. We're not doing a graph yet. Second thing, everyone loves using a calculator. So let's use a calculator. So specific heat of water. Now I do need to be more specific. H2O is the symbol for water. It's the chemical symbol. Chemical nomenclature. What's the right word? I haven't had chemistry since early 80s. H2O, that's considered the symbol, doesn't seem quite right, nomenclature, shorthand.
Shorthand.
Shorthand, we'll go with shorthand. So that's the shorthand for water, H2O. That always bugged my mom, she always felt it should be H. But, you know what, you're not here right now. So, maybe she is. So, well, you know, I've gotten a whole lot better about not sort of cheering up, but occasionally it just hits. All right, so specific heat of water, first of all, what units we want to use. Oh, that's right, that's where I was going. What are the three major types of water that we deal with?
Solid, liquid, and gas, is that?
Okay, yeah, but what are they called in solid form? What's it called? In gas form?
Yeah, vapor.
Steam or vapor, there is a subtle difference between the two, but I'll take either right now. So when I just say water, I really need to be more specific.
You refer to matter in general, or is that not that?
Yeah, but typically, if I'm talking about, I've got an aluminum, if I have a piece of aluminum here, I suspect you're not thinking about anything other than it's a piece of metal, solid form. We typically don't deal with most of these things in any other form other than its natural form. Water is a little bit different in the fact that we do deal with ice, liquid, and steam/vapor. That's why I really should be more specific here. So in liquid form, that's an L in parentheses. See if I can actually write that more legibly.
So, is that CH2O on the board? Specific heat?
That's C with a subscript of H2O, meaning water in liquid form. That's an L.
Which of these is
So specific heat of water in liquid form.
Yeah, I haven't finished it. I'm gonna write a number down in just a moment. But this is the specific heat of liquid water. It is, there we go, 4.1813 joules per gram degrees Celsius. Ish. I've seen a couple different numbers for this. The specific heat changes depending on the temperature of water, liquid water. So I got 100 degrees Celsius through which I can deal, and it does change slightly. So there'll be other times I'll put a slightly different number down. Now recognize that when you were pre-internet, pre-mass communication, when you are establishing your basics, when you are trying to set up something that is going to be used, it's convenient to set a standard based on something everyone has. At least from the Europeans' point of view, everyone had access to water. And so they had to establish a standard based upon water, and so the specific heat for water in a different unit system is 1 calorie per gram degrees Celsius.
What'd you say again?
So, since water was considered universal or global, that they established what the calorie is, calorie per gram degree Celsius for water is 1. That was awkward sentence construction just then. But the specific heat is 1 calorie per gram degree Celsius. In essence, they're defining a calorie to be the amount of energy I need to change 1 gram of water 1 degree Celsius. And then later on, when joules were created, they had to come up with a conversion between the two. All right, so I've got liquid water in a container. And let's say I've got 50 milliliters of water at 20 degrees Celsius. And I want to get that water up to 60 degrees Celsius. How much energy do I need to put into that water in order to do it?
Would it be 40 degrees?
That will be the change in temperature. So, well, let's start with basics. I'm trying to figure out how much energy to put into something, not changing phase. All I'm doing is changing the temperature. So I've got my Q is equal to MC delta T. And so delta T is 40 degrees Celsius. C, which unit system do you want to work with?
One.
I heard calorie. All right, so yeah, 1 works. 1 calorie per gram degree Celsius. And then the mass. How much mass is 50 milliliters of water? It actually will not take, you will not need a calculator for this.
Is it the same?
Numerically, yes. Unit-wise, no.
Okay, so 50 kilograms
5 kilograms.
of grams, 50.
Yeah, 50 grams.
Okay.
This is another one of those things with water. When they were establishing densities, when they were establishing mass, they basically said 1 milliliter, which is 1 cubic centimeter, of water has a mass of 1 gram. And so now they can establish some sort of standard across the world. So that is 50 grams
You said 1 milliliter?
of water has a mass of 1 gram. Ish. You know, you establish the convention, and then as you get more and more sophisticated methodologies, you suddenly realize, okay, it's good enough for what we're doing, but we're not designing multi-million-dollar experiments. And so the fancy math here, 50 times 1 times 40, and we end up with 2,000, yeah, 2,000 what?
Two.